Hi again. In this lesson, we shall discuss the phenomenon of electromagnetic induction. Throughout our quest on the electromagnetic field and its applications, we discussed how a changing magnetic field produces an electric current in a conducting wire. In this lesson, we shall look at a practical experiment to verify this. The principle behind using a magnetic field to create an electric current in a wire or coil is called electromagnetic induction. The word induction refers to the process of bringing about something. So, electromagnetic induction means the process of bringing about an electric current or voltage in a conducting material by moving it in a magnetic field. You should already know what a galvanometer is. But if you don't, you can check out our lesson on the moving coil galvanometer. A galvanometer is an instrument used to detect the presence of an electric current. So when you attach a galvanometer to a power source like a battery, you'll see the pointer of the galvanometer move and record a reading on the galvanometer scale. Now, when you disconnect the terminals from the battery and attach them to a coil as shown, it will not read current at first. But something amazing happens when you bring a magnet close to the coil. As you can see, a tiny reading is recorded on the galvanometer. What you notice is that the pointer makes a quick reading and then goes back to zero. This implies it has induced a small current in the coil. But wait to see what happens when the magnet is pulled out. Did you see that? Not only did the pointer move, but it moved in the opposite direction. So I want to ask, why did it move in the opposite direction? The answer is in Fleming's right-hand rule. You can check this out in our lesson on the magnetic force in a loop. When the magnet was first brought close to the coil, the magnetic field was in this direction, and that made the current to flow in that direction. But when the magnet was pulled out, the magnetic field was reversed, and the current flow was in the opposite direction. Now let us keep the magnet stationary and move the coil instead. When you move the coil this way, a current is induced in the coil and you will notice a deflection. When you move the coil in the other direction, the pointer also moves in the opposite direction. What this implies is that as long as the magnetic field is changing, there will be an induced current generated in the coil. But when the magnet and the coil are stationary, then there is no induced current. So we can say that an induced current can only be generated in a wire or a coil when there is a changing magnetic field. So we shall look at some of the laws governing electromagnetic induction in our subsequent lessons. Bye for now.